Hello everybody, Programmer53 here. Get excited because today we're going to be talking about bioinformatics FASTQ files. But before we go into the file format, I want to quickly go over the origin so we have some background. The file format was developed at the Wellcome Trust Sanger Institute to bundle biological sequences, so nucleotides, and the quality of said sequences in the same file. They serve as the de facto standard file format for the output of high throughput sequencing instruments. So yeah, better origin story than Wolverine. Also, I want to mention before we go through the FASTQ file format and into an example, is that usually they're not necessary to view because they serve mainly as the intermediary step for eventual downstream analysis to produce something like either a reference genome, which would be stored in a FASTA file, or reads for a transcriptome, which would be found in a SAM file or a BAM file. And the reason I mention this is that although FASTQ files are technically human readable, they're not exactly human friendly, sort of like the R programming language. Okay, without further dilly-dallying, let's look at an example of a FASTQ file. Here's an example of a FASTQ file in its simplest form. In this instance, we're looking at a FASTQ file that only contains one read or one entry, which is pretty unusual for a FASTQ file, but useful for educational purposes. Okay, so in order to understand this FASTQ file, let's work our way from top to bottom. So this first line starts off with this @ character and is preceded by this sequence identifier, so this SRR00 and some other stuff. The sequence identifier must be unique for each read in the scope of our file. So in this case, we only have one read and thus one sequence identifier, but if there were multiple reads, which we'll go through an example of at the end of this video, there'll be a unique sequence identifier for each read. The sequence identifier is followed by a space and then by a description for the read in question. So it usually has some sort of useful information about the read. Line 2 contains the raw read, or the base calls that were interpreted by the machine, ergo why you see the ACGT nucleotides. Line 3 starts off with this plus sign and then is optionally preceded by the sequence identifier and description that we saw on line 1. So I say optionally because a lot of FASTQ files actually omit this data because it's redundant. But I would exercise caution if you are handed a FASTQ file that doesn't have this data in it and elect to remove it, as it might have some sort of an effect on downstream analysis. So just be careful. Line 4 is simultaneously the most interesting and confusing. It contains the quality scores for the sequences in line 2. Each of these characters represents a different quality score for the corresponding base call at the same index. So for example, the quality score at index 0, which is an I, corresponds to this base call of G at index 0. Because there is a quality score for each nucleotide, the length of characters on line 4 is going to be the same as the length of the characters on line 2. The quality scores ultimately represent an interval of confidence for each base call in the sequence, and normally I wouldn't go over how to convert these quality scores into these confidence intervals because it's a little bit esoteric, but the quality scoring system is used in other bioinformatics file formats like SAM files, so theoretically it could be useful in the future. Okay, so how do you do this? Let's go through an example and find the probability that the base call for the first base, so in this case G, is incorrect, working our way back from the quality score of I. First, we start off with the equation to calculate the quality score, which is Q here, but remember we want to calculate P, so the probability that the corresponding base call is incorrect. So we're going to need to rearrange the equation by dividing each side by -10 and taking 10 to the power of each respective side to cancel out the log 10, and we end up with our equation for P. Now all we need to do is plug in the integer quality score, so Q for our character, which remember is I. And to do this, we're going to use an ASCII table to derive that value. Okay, so now we're looking at an ASCII table that I found online. The quality scores in the FASTQ file can range from exclamation point, which has a value of 33, to tilde, which has a value of 126. The quality scores start from 33 or exclamation point because the first 33 ASCII characters are all non-printable. Remember this, it will be important in a second. So for example, again, our quality score is I at 73. Great, so we can just plug in 73 as our number for the quality score in our equation, right? Actually, not quite yet. The quality score needs to start from 0 for our formula to work because, again, the quality score skips the first 33 values of the ASCII table. So we have to minus the first 33 ASCII values that we skipped, which gives us a value of 40, as in 73 minus 30. Okay, so altogether the formula for P will look something like this. And then we can plug our quality score of 73, which corresponded to I in our formula, to end up with a value of 10 to the negative 40, as we talked about before, divided by 10. And then after we plug this in, we find that P, again, the probability that the base call is incorrect with a quality score of I, to be 0.01%, or 1 in 10,000. Great, so we totally know how to calculate the probability that each base call is incorrect, except maybe not, just heads up. The formula that I showed you for the calculation is usually the right one. So again, this formula for the quality score is usually right, but not always. Depending on the machine that was used, there can be slight variations of this formula. So it's important to understand the machine the FASTQ file originated from if you want to calculate the quality and or probability that the base call is incorrect. Remember, this is bioinformatics, a lawless wasteland of the highest caliber. And one last thing that I want to address before we wrap up this video. In the example we looked at earlier, we looked at a FASTQ file that only contained one entry or one read, but pretty much all FASTQ files are going to hold multiple reads. That's going to look something like this, where you can just stack the other reads on top of each other using the same format that we discussed earlier. And remember, the sequence identifier for each read needs to be unique.